Hello and welcome to the Further Maths Support Programme's core revision recordings. Today we're going to be looking at A2 differentiation topic, and we're going to be starting specifically with the chain rule and the product and quotient rules. The other topics are going to be available in future recordings. We're just going to focus on these two areas for today. Okay, so where do we use the chain rule? First of all, the chain rule tends to be used where you're dealing with a composite function. And a composite function is one where you have an inside function. In this particular case, we've got x squared plus 5 is the inside function, and an outside function, which in this case is the cube. When you're using the chain rule, the theoretical version of it is that in order to differentiate y with respect to x, you can first differentiate it with respect to t and then multiply by dt dx. And that's often calculated as dy dt divided by dx dt. But we can think of that more simply as differentiating the outside function, differentiating the inside function, and then finding the product of the two. So let's do that for this expression that we've got here. We're differentiating x squared plus 5 all cubed with respect to x. If we differentiate the outside function, remember that's the cube. Differentiating a cube, you put the power in front, and we're just writing the bracket exactly as it was before, and you reduce the power by 1. So that's the differentiation of the outside function. We're then going to differentiate the inside function, so differentiating x squared plus 5 gives us 2x, and the product of the two gives us our complete derivative. So simplifying that gives us 6x times x squared plus 5 to the power of 2. That's our derivative. Okay, so let's take a look at some examples here. All the way through this recording we're going to be using these multiple choice questions, so if at any point you want to have a go at the question yourself, you can stop the recording and just have a little go at the question. I'll be continuing with the explanation, so if you want to pause at this point and restart when you're ready to hear the explanation. Okay, so we're differentiating the expression 2x plus 1 to the power of 4, and we're differentiating that with respect to x, so d by dx of 2x plus 1 to the power of 4. Differentiating the outside function in this case means differentiating the power of 4, so the power goes in front and we reduce the power by 1, so 4 times 2x plus 1 cubed. We then need to multiply by the derivative of the bracket, which in this case is just 2, and we can simplify to give us 8 times 2x plus 1 to the power of 3. That's our derivative in there, and that matches nicely with answer C in this question. Let's take a look at a second example. Now this expression here, the outside function, is perhaps a little bit more difficult to see, but if we say that we're actually differentiating the expression x squared plus 1 to the power of minus 1 here, you can then see that the reciprocal is the outside function, that's the power of minus 1, and the x squared plus 1 is the inside function. Differentiating, power in front, and reduce the power by 1, that's the outside function differentiated, multiply by the derivative of the inside function, which in this case is 2x, and then we simplify back into the original form of the question. That leaves us with a negative from the minus 1 here, times 2x over x squared plus 1 squared. That's making that negative index there back into the reciprocal down at the bottom here, and so we can see again in this question that part C is our correct answer. Okay, this is an application of the same technique. So we have a curve y equals 1 over 1 minus 2x, and we're looking for the gradient of the tangent, we're looking at the equation of the tangent at the point where x is 1 and y is minus 1. We need to know the gradient in order to be able to find that equation, so I'm going to calculate dy by dx. So dy by dx is the derivative with respect to x of our function here, which I'm going to rewrite as 1 minus 2x to the minus 1, a little bit like the previous example that we did. If I differentiate that, power in front, reduce the power by 1, multiply by the derivative of the bracket, and if I simplify that, that gives me 2 over 1 minus 2x squared. So that's my gradient function for the curve. When x equals 1, the gradient, I'm just going to shorten that to m for the purposes of this question. When x equals 1, the gradient is going to be 2 over 1 minus 2 all squared. So that's 2 over negative 1 squared, which is 2 over 1, which is 2. And then you can use a formula for the equation of a straight line, whichever one you're used to using. I'm going to use y minus y1 is mx minus x1. In this case, that's going to give me y minus minus 1, so y plus 1 equals 2x minus 1. And you can simplify that out by expanding the brackets, taking the 1 over to the other side, and that's going to give me y equals 2x minus 2 minus another 1 makes minus 3. And that matches with our answer B here in the question. Okay, so here's a proper application of the chain rule. This type of question, sometimes it's a little tricky to see what the actual values and variables that you're given are in here. So let's read this carefully. When a light source is r centimetres from a point O, so we're told that we have r as a variable. The light intensity at O is 100 over r squared lux. Okay, so we are defining here light intensity also as a variable. Now, no letters given for light intensity in this question, so I'm going to say that light intensity is represented by capital L. So I have a formula for capital L in my question already. I know that capital L is 100 over r squared. It then tells you then that when r equals 5, let's just make that a boundary condition. When r equals 5, the light source is moving away at a rate. And as soon as you see that word rate, you know you've got d by d something. Okay, so light source is moving it away at a rate of 0.5 centimetres per second. So that's a distance per time. This is d something by dt. And the light source, the distance of the light source away from point O is given by r. So we know that we've got dr by dt here is 0.5. The distance between them is increasing at a rate of 0.5 centimetres per second. So rate of change of r, dr dt is 0.5. Okay, so we've written down all the information that we've been given in the question. We're being asked then to say the light intensity is changing at a rate of. So we're looking for the rate of change of light intensity. We need dl by dt. Okay, so that's what we're looking for. Well, let's have a little look at how we could use the chain rule to get this. We know that we're looking for dl dt, and we could use the chain rule in its classic form here. We could rewrite this as dl dr times dr dt. Chain rule tells us that that's valid. And we already know dr dt because we were given it in the question. All we need is to be able to find dl dr. Well, we know L in terms of r here, so let's just rewrite that in a form we can differentiate. That's 100 r to the minus 2. That means I can differentiate to get dl dr. That's going to be minus 2 times 100 r to the minus 3. So that gives me dl dr is generalized to minus 200 over r cubed. So I can then say when r equals 5, dl dt, which is what we're looking for, is given by dl dr, which is minus 200 over, in this case, 5 cubed, which is 125, times dr dt, which we were given to be 0.5. And if we simplify that down, stick that into a calculator, you can see first of all it's negative, so both of these positive answers are going to be no use to us, and a quick work on your calculator should show that that comes out at 0.8, negative 0.8. So our answer here is B. Okay, so here's a little enrichment nugget related to the chain rule. This may not necessarily immediately seem to be connected with chain rule, but I hope I can convince you that it is. I'd like you to imagine that cog A here is turning at a constant rate omega, and you can see it's turning in this clockwise direction. I hope you can imagine then that that's going to cause cog B, which is connected to it, to turn in an anti-clockwise direction, and each of the cogs then are connected in this alphabetical order through this whole range. You can see A turns B, B turns C, C turns D, D turns E, all the way down, H turns I. Okay, what I want to know is if A is turning at this constant rate omega, what rate is I going to be turning in? So A is going in the clockwise direction at rate omega, what direction will I turn in? Okay, so let's take a look at adding some extra information on here. I think you can probably see that the number of teeth on each of the cogs has a bearing on how they relate to each other. So I've shown here that I've counted up A's cogs, it has 16, sorry, A's teeth, it has 16 teeth, B has 8 teeth, C has 8 teeth, D only has 6 teeth, E has 8, F has 16 again, G has 8, H has 6, and I has 8. So what that means is that as A turns around, B is going to have to turn around quicker than A in order for it to, if you like, for it to mesh with A. As A makes one full turn, B is going to have to make 2 full turns in order for its teeth to remain meshed with A's. So what that means is that we've said that the rate of turn for A is omega, so dA by dt is omega. dB by dA is -2, and that's because first of all B has to go in the opposite direction. So if A is going clockwise, B is going to have to go anti-clockwise, and also for every turn that A makes, B is going to make 2 turns. So I hope you can see there that dB by dA, that's the rate of turn of B with respect to A, is -2. And here's where your chain rule comes in. If dB dA is -2 and dA dt is omega, then dB by dt, the rate of turn for B, is going to be dB dA times dA dt. That's our chain rule calculation. So dB dt can be given by -2 omega. Okay, and we can carry that through the rest of the calculation. If we have a quick look at C, now C has exactly the same number of teeth as B, so dC dB is going to turn at the same rate, but just notice C is going to turn in the opposite direction to B. As B goes anti-clockwise, C is going to go clockwise, so dC dB is -1, which means dC dt, let's use our chain rule here, is going to be dC dB times dB dt, and we can pop our information that we've got into the calculation there. dC dB times dB dt, so -1 times -2 omega. The rate of turn for C is going to be 2 omega, so the same direction as A, but twice as fast. And you can carry that calculation through the remainder of the turns. Let's take a quick look at D. Now, as C is turning clockwise, D, you see, has to turn anti-clockwise, but D's only got 6 teeth. So let's just have a little think about dB, sorry, my mistake, dd, sorry about the slightly tautology in the notation here, dd dc, it's going to be the negative of the rate of turn for C, because they've got to go in opposite directions. So each time you go from one cog to the next, the sign is going to change. All right. Now C has more cogs than D, so C is going to turn slower than D, or D rather is going to have to turn quicker than C to keep up, as it were, to keep meshed. And you can see here we've got this kind of gear ratio of 8:6 between C and D, and that can be simplified down to a ratio of 4:3. So the rate of change of D with respect to C is 4:3. D will make 4 turns to every one of C's, and as we said before, they've got to be in the opposite direction. That means dd by dt is going to be, and just using chain rule there, dd by dc times dc dt, so -4/3, and dc dt we said was 2 omega. So the rate of turn for D then is going to be minus 8 omega over 3. Okay, so you can see there that D is going in the opposite direction. It's going anti-clockwise, opposite direction to A, and it's going a little over twice as fast as A is moving. You can continue this calculation all the way through, working through E connected to D, F connected to E, and so on, and eventually you should be able to find the rotation for I, and I think you should discover that I ends up going in a clockwise direction, and it should be moving, oops, my mistake, sorry, and it should be moving clockwise at 2 omega, but you can check that for yourself. Okay, let's turn on then to product and quotient rules. Okay, so the product and quotient rule is used in the type of function where you have a product of two functions or a quotient of two functions, so sort of the clues in the name there. So a product may look something like this. So for example, you could have 2x squared multiplying x plus 5 to the 4, and in this case you have two clear separate functions multiplied together. 2x squared could be u, x plus 5 to the power of 4 could be v in that case. Now for the product rule, this product rule is something we call commutative. That means that in actual fact I could treat this first one as v and the second one as u if I chose to. The two are interchangeable in here as long as you consistently put the derivative of one with the non-derived version of the other. I like to try and remember the product rule in the order that it's shown on the screen though, and the reason I like to remember it like that is because I think it then helps you to remember the quotient rule more clearly. In the quotient rule, it's important to get u and v the right way around. U has to be the numerator and v has to be the denominator, because otherwise the quotient rule will fail on you. It's a non-commutative function. So quotients, something along the lines of, let's have x plus, let's have 3x plus 5 over x squared minus 1. For example, this would be a quotient, and we would take 3x plus 5 as being u, and x squared minus 1 would be v, and you can't interchange those two. Alright, so let's have a little look at the product and the quotient rule working. Okay, so we're differentiating here x squared times 2x plus 1 to the power of 4, and first of all we need to decide which is our u and which is our v. So I'm going to take this one classically as u first, followed by v. Okay, so using our product rule here, we're going to calculate v. So we don't differentiate it to start off with, we just write v as it is in the original term. We multiply that by the derivative of u, so that gives me 2x, and then we're going to add u, which is the x squared bit, multiplied by the derivative of v, so 4, and this is using the chain rule here, just as we saw in the previous section. So 4 times 2x plus 1 cubed, that's the outside function differentiated, and we've got to multiply by the derivative of the inside function. Very often these questions, the actual application of the formula is the easy bit. It becomes tricky then when you are asked to simplify a little bit, so we need to make our answer look like one of the expressions that's one of the options that's available. Okay, so just simplifying a little bit there, this is a two-term expression, so we have one term here and a second term here. There are some similarities between those two expressions, and we can use that to factorize the two expressions. So I'm going to take a factor of 2x, because that appears, if you like, in both parts of the polynomial here. I'm also going to take a factor of 2x plus 1 cubed outside a bracket, and then inside a big bracket I'm going to put in the terms that will make each of these come back to where they should be. So starting with, we need a 2x plus 1, that would multiply our 2x plus 1 cubed here to make our 2x plus 1 to the 4 above, and also inside that bracket, sorry I didn't want that bracket there, let me just get rid of that. Okay, so the 2x plus 1 from the first term, and then I also want a 4x, because the 4x would multiply the 2x here to make my 8x squared in here. And when I simplify that down, then I can just tidy up that last bracket, 2x plus 1 cubed, and that final bracket becomes 6x plus 1, which I think you can see here in part D of the options. Okay, let's try a quotient. Now, you could treat this quotient rule question actually as a product rule. You could rewrite it as x squared times 1 minus 2x to the minus 1 and use the product rule in order to differentiate that. We're not going to do that in this particular case, but just so you know that that is also a valid option for this type of question. Okay, but I'm going to use the quotient rule for this one. Numerator is u, denominator is v, and here we go, applying the formula as it comes in. So we start with v, and then du dx, and we subtract u, that's the x squared, dv dx, so differentiate the denominator and you just get minus 2, and that all goes over v squared, 1 minus 2x, all squared. We can simplify that down, expand the brackets on the top line there, and I get 2x minus 4x squared, minus 4x squared plus 4x. Have I made a mistake somewhere along the track? Nope, I think that's okay. Minus 4x squared, minus 4x squared plus 2x squared in the numerator, and in the denominator we can put our v squared. Let's simplify that top line a little bit. 2x minus 2x squared all over 1 minus 2x all squared, and we can factorise just to tidy it up a last little bit. 2x outside the bracket, 1 minus x inside the bracket leaves us, and the bottom line 1 minus 2x all squared. Okay, so that's our answer in there, and I think you can spot that that matches nicely with answer A. Okay, so a little application of product or quotient rule. In this case we're going to use the quotient rule. So we're being asked here to find the turning points on this curve. So in order to find the turning points we need to know where the gradient is 0. So we're going to differentiate 3 plus x squared over 1 minus x, and we're going to do that using the quotient rule. So my numerator 3x squared is going to be u, and my denominator 1 minus x is going to be v. So dy by dx, my gradient function for the curve is going to be v du dx minus u dv dx all over v squared. I'm going to tidy this up quite a bit because I'm going to need it again later on, and you'll see the reason for that shortly, but I'm just going to put this as neatly as I can. So expanding the brackets in the numerator, 2x minus 2x squared plus, and just be careful with those double negatives here, 3 plus x squared. Bottom line remains 1 minus x all squared. And I think I can just squeeze this in on the top line here. I think that leaves me with 3 plus 2x minus x squared all over 1 minus x all squared. Okay, so that's my gradient function. The gradient function is going to be 0 at the turning points. Okay, so I want to evaluate at turning points. I want to make this equal to 0. So I'm making 3 plus 2x minus x squared all over 1 minus x squared. I'm going to make all of that equal to 0. We can multiply it by the 1 minus x squared and eliminate it, so we don't have to worry about that in this part of the calculation. That means I've got this quadratic x squared minus 2x minus 3 equals 0. I can just do a quick factorise on that, x minus 3 and x plus 1. That tells me then that x equals 3 or x equals minus 1. I think that eliminates a couple of the possibilities on here already. There certainly are some turning points, and there are only 2, so it can't be answers C or B. We can find our y values here. Let's just put those in. You may have noticed actually the y values are the same in both the remaining options, but let's just do this for completeness. When x is 3, y, that's substituting back into here, y is going to be 3 plus 9 over 1 minus 3, which is 12 over minus 2, which is minus 6. And when x equals minus 1, y is going to be 3 plus minus 1 squared over 1 minus minus 1, which gives me with 4 over 2, which is 2. So our two turning points we now know are 3 minus 6. And if you're asked this in the exam, don't forget to write the actual coordinates down rather than just finding the values and then leaving the examiner not sure which ones go together. But there we go, we have our turning points, but we need to distinguish between these points being maxima or minima. So let's just hop over to the next page. I need this expression here on the next page, so I know that I've got dy by dx is 3 plus 2x minus x squared all over 1 minus x all squared. That was my differentiated expression. Now I've got lots of choices here. I know that my points are minus 1, 2 and 3, minus 6, but I don't know whether they're max or min. So I've got lots of different ways of choosing this. I could consider points slightly either side of x equals minus 1 and see whether the gradients change from positive to negative or vice versa. Another alternative is that I could differentiate again and find the value of the second derivative, and I'm going to do that just so that I can use my chain rule again. So if I want to know d2y by dx squared, I'm just going to change the ink colour here for a moment, and this time I'm going to make the top line of this expression u and the bottom line v. Alright, so now, oops, sorry, let me just change that colour back. Okay, so differentiating use the chain rule this time is going to give me v times du dx, that's differentiating that numerator there, minus u, this is going to be a bit crowded, dv dx, and we're going to use chain rule here, 2 lots of 1 minus x to the 1, and we've also got to multiply that by negative 1 because that's the inside of the bracket, all over, please excuse my slightly crowded working, 1 minus x to the 4, that's 1 minus x squared, squared. So d2y by dx squared here, and there's a whole lot of stuff to simplify on that top line there, but essentially you can now either expand that and simplify it, or if you choose to, you could take your value of minus 1 and you could just replace x with minus 1 in here and here and here and here and here and here, and essentially if you can evaluate that, if d2y by dx squared is greater than 0, I'm sure you're aware, this implies that you've got a minimum, and if it's less than 0, then you have a maximum. Okay, so that gives you another option of how to choose between those points, and it's a nice application then of the quotient rule used twice over. Okay, so that's all that we're going to look at today. If you're interested in details of further online or face-to-face revision events, or you're interested in any of the enrichment or CPD activities that the FMSP is involved in, please do take a look at www.furthermaths.org.uk. If you go to that website, you'll be able to navigate to your local region as well and see what events are actually going on in your area, and as I say, there's lots of other online material available. I hope you found this useful and look forward to working with you again.